Welcome back to part 4, The Road to Digital Automation at Toyota, Learning How to Be an Informed Consumer. Part 4, Making Decisions and Probabilistic Forecasting. So making decisions involves turning the information into a decision. We make decisions using a policy, but that raises the question, what do we mean by a policy? So a policy is a method that makes a decision using the information in the state variable. And I mean any method. Now, so far I'm up to 49 different words in the English language that in the right context refer to how to make a decision or guiding people to make what decision. So I like to think of this as like a locomotive for companies. Steam engines turn the energy in coal into a force that propels the train forward. Policies are the engines that turn information into decisions to drive companies forward. So information is like the energy going into the engine, but information is very different than coal. Information is more like a buffet and the food going into a person, and of course the engine is a computer. And it's the intelligent computer models that are turning this information into decisions. So there are two fundamental strategies for designing policies. The policy search strategy involves creating functions that are tuned to work well over time, and the look-ahead approximations where I make decisions by planning into the future. Each of these I'm going to divide into two classes, creating 4 classes of policies. So let's start with policy search. So policy search is any rule, order up to inventories. When the inventory goes below some number, order up to another number, buy low, sell high in finance. If it's cold, wear a coat. Policies can be lookup tables. They can be linear, nonlinear models. They can be a neural network, any function we might use in machine learning. Now, the second class is cost function approximations. Now, this is when we take a decision problem and actually solve it using an approximate optimization problem. So we simplify in some way, but then we insert tunable parameters to make it work better. So one example is shortest path problems. Okay, so I'm willing to let Google Maps figure out a shortest path, but I also have to decide when to leave so I make it in time for my appointment. Now, Google Maps is telling me 40 minutes, but I'm scratching my head going, I'm not so sure because I know about traffic. Maybe I'll allow 55 minutes. Now, if this is a trip I do over and over again, I may learn that the 15 minutes is too much or too little, and I have to adjust it. I might be optimizing facilities, and what I have to do is I don't want to plan facilities hitting 100% capacity because I'm actually not that sure about the flows, and I'm going to put in a buffer compound. Now I have to tune the buffer so that it works well over time. Now, another nice example is this one at the bottom where let's imagine I'm Google or Facebook or any e-commerce, and I want to put up ads, and I want to pick the ads that get the most clicks. So let's say product X. Maybe products X is A through G, but it could be thousands of products. And I want to find the one with the highest expected revenue when people click on it. And I have estimates, but they may not be very good estimates. So I have a point estimate. I have my estimate of how much money I'm going to make, but I have what's called a standard deviation, measure the spread. So what I'm going to do is take my estimated revenue and add in some number of standard deviations, maybe 0, maybe 1, maybe 2, maybe 1.5, and I have to figure out what that tunable parameter is. And tuning that parameter is actually quite important. So those are my two policy search policies. Now let's look at the look-ahead approximations. So these are going to be for a little bit more complex problems. I like to use the example of Dorothy finding her way to the Wizard of Oz, where she gets to this intersection and she has to figure out what direction to go, but she has to think about eventually getting to her destination. So one way to do that, let's take this problem that we run into at Optimal Dynamics of optimizing fleets of trucks. So I'm assigning drivers to loads, but what I do on Monday can impact Tuesday. It changes what drivers are available and where they are, and that impacts Wednesday. And it's one thing to optimize the problem on Monday using what I know, but I have to think about what might happen on Tuesday and Wednesday, and it's high dimensional, and it's stochastic, and it's ugly, and it's hard, and I have to solve it quickly. So what I'm going to do is to say, you know what, let's just approximate Tuesday and Wednesday. What I really need to do is to say, if I assign a driver to load, now the driver is going to go to Chicago. What's the value of that driver in Chicago? So that value of driver in the future is like estimating the value of being in a state. And I can't get that exactly, but I can get what's called a value function approximation. Now, There's a lot of technical stuff going on in getting that value function approximation, but once I have it, my problem on Monday now becomes really easy. So this is something that we actually use at Optimal Dynamics. And I studied this for many years. I have a 600-page book on this. I'll come back to this type of policy a little bit later. Now, what often happens is I think about the first three classes of policies and I scratch my head and I realize, no, that it's not really working. The fourth class here is what you do when all else fails, and I like to say, and all else usually fails. Okay, let's imagine. So I'm up in Hartford, Connecticut, upper right-hand corner. I'm trying to get down to my home in Princeton, lower left-hand corner, and I'm leaving at 4 p.m. and I'm saying, hey, Google Maps, plan me a path home. And it says, hey, I've got this great path. By the way, it's going to go through New York City at 5 p.m. Now, this is a look ahead policy. I'm planning into the future. Now, there's uncertainty, but Google ignores that. It uses its best estimates. Now, you can call this a look ahead policy, but if you want to be fancy, the controls people call it model predictive control. Okay, whatever. Now, of course, I'm looking at New York and going, oh, wait a minute, New York at 5 p.m., really, Google? So Google does give me an alternative path. So what I'm doing is saying that alternative path is longer, not very much longer, but I avoid that risk of the uncertainty of going through New York. Now, I'm actually, in an ad hoc way, I'm using a technique called robust optimization. There's a whole book on that. Now, I can use other things, stochastic programming, or even my book, Approximate Dynamic Programming. And what you've got here is 4 entire books dedicated to specific ways of planning into the future. So this is our fallback. Now, most people in practice do the deterministic look ahead, but there are going to be times when you have to deal with uncertainty. Okay, so I have now given a very quick tour of the 4 classes of policies. The policy search policies are the simplest, the PFAs and the CFAs. The look-ahead policies are inherently more complicated. The VFAs, you have a lot of work to get those value functions. Direct look-aheads come in 2 flavors, deterministic look-ahead like Google Maps, and stochastic look-ahead where you explicitly model the uncertainty. Now, we have used all 4 classes in this talk. We've got our order up to, we have the CFAs where like we put an optimistic estimate on the value of a product, we have the value of drivers in the future, and we have our Google Maps. These are all types of policies that I'm going to argue that we humans actually use all of this stuff, and somehow we may not recognize that we're using it, but our brain is able to switch and identify it. Now, something that can be confusing is that these policies are all trying to solve a decision problem. 3 of the 4 classes of policies are themselves optimization problems. So finding the best policy is an optimization problem. 3 of the 4 classes are themselves optimization problems, and this is something that can be very confusing to many people. Now, most important, I'm about to make a very big claim. These 4 classes of policies are universal. They cover every method for making decisions described in the research literature or used in practice, including any method that you haven't even invented yet. That's why we call them meta classes. It also means that you can't go out and buy one of these classes. Each of these classes describe, like an entire category of car or an entire category of food. So it does mean that when you go into a company and say, well, how are you solving the problem now? That's a starting point. It's in one of the 4 classes. Now, I may want to do hybrids. I can do mixing and matching. Now, you can't do mixing and matching unless you know about all 4 classes. Here's a little example of an energy storage problem. So I can pull energy from a wind farm. It's free, but highly variable supplies. The grid, for my purposes, I can think of the grid as infinite supply, but the price can be highly random. I'm meeting some load that is fairly predictable, and I've got my Tesla Megapack to absorb ups and downs. Now, what we did in the lab, this is joint work with Stefan Meisel at University Twente. Stefan created 5 variations of this problem, and we knew what we were doing. Then we created 5 policies, the first 4 from each of the 4 classes, and the 5th was a hybrid. Now, the numbers in the squares indicate how well it worked. Yellow is best, and we've made each of the 5 classes of policies work best on one of the problems. Now, that's not going to be true for every sequential decision problem. Some problems are just going to be naturally solved with one of them, and it'll be obvious to you, but not always. Now, let's say we have a logistics problem. I'm getting my product from Asia, but I might have a hurricane. I don't know for sure, but I do have the option of air freighting the freight in. My PhD student, Shahe Lu, created 6 variations of this logistics problem. She also created 4 different policies. Once again, yellow means this worked best, tan means second best. Now, the first policy is a textbook order up to policy. If the inventory goes below one number, you have to order up to another number. Now you have to tune those little s and big S, which actually is quite hard. The second one is one of the most popular policies in the inventory literature and in practice, where there's an adjustment for lead times, and the lead times can be random. Once again, you have tunable parameters, and I might note that that policy, if it's not best, it's second best on all of the problems. That doesn't mean that it's very good. It just means it can be second best. The third one is direct look ahead, deterministic look ahead. That's like Google Maps, where we look forward, but anything that's uncertain, we just take a point estimate. And the fourth one, we actually model the uncertainties. So that's the stochastic look ahead. Now let me go back to this general area of bridging machine learning and sequential decision problems. I want to once again review objective functions. So with machine learning, what we're trying to do is to minimize the error between my function, which could be a linear function or a neural net, versus my observation. So I'm trying to minimize the error. With sequential decision problems, I'm trying to optimize some performance metric, profit, minimize cost, whatever, but I have to give it the metric, and I have to model how the system evolves over time. So I've got the actual physics of the problem in my model, which I don't do under machine learning. Now, when I compare these two with machine learning, I'm looking over functions. Those are the different classes of functions. With sequential decisions, I'm also searching over functions. We call them policies. With machine learning, I have training data sets. That's the only way that I can communicate an actual application. Whereas sequential decision problems, I do not use a training data set. I use a model of the problem. Now, when I go to doing my policies, one class uses anything from machine learning. So all of those 3 circles of functions, that's my library of functions if I stick with PFAs. It turns out that's a fabulous class of policies for many problems, but not all. I then have the other 3 classes, all of which are optimization problems. So clearly in sequential decisions, I go looking at a much richer class of policies. So one idea is to take policies and think of them as something like a robot, and I have PFAs are the very simplest type of robot, CFAs a little bit more complicated, VFAs a lot more complicated. DLAs, I have 2 robots because you've got really 2 ways of looking into the future with direct look aheads. You have the deterministic look ahead, that could be like the R2D2 one, or a stochastic look ahead might be more the humanoid robot. Now, here's something that I really couldn't do until the end of my career. Which one of these are most useful? So let's identify 5 types of policies, the 4 classes, but let's split that 4 classes into 2 types, the deterministic look ahead and the stochastic look ahead, and ask a simple question: which are most useful? So I created category 1. I claim this covers probably 97% of all decision problems: PFAs, CFAs, and deterministic DLAs. All humans use these. You use these maybe without even knowing it. This is your go-to set of policies for making decisions, because we've been making decisions for, I don't know, the last 200,000 years, and we've done it up until a few decades ago without the use of computers. Now, category 2, stochastic look ahead, that would be like Google Maps, where I'm uncertain about going through New York City. Uncertainty happens, and we humans deal with it, and we know what to do with it. Finally, we get to category 3, and that's the policies based on value function approximations. Now, let me remind you, I wrote a 600-page book on that. I spent 15 to 20 years of my life. I've put a lot of time into VFAs. I've got them at the bottom of the list. And I think I can pretty safely say this is a very powerful strategy for a very small number of specialized problems. And probably we humans from time to time use something like a VFA, but to put it on the computer is hard. Now, people often ask me, how do I choose the policy class? And I'm going to answer by showing you some screenshots out of my technical book. So this is my advanced book, and I have a section called Choosing the Policy Class, and I have a subsection on screening questions that I ask. And one of the first screening question I ask is, does the problem have structure that suggests a simple and natural decision rule? In other words, in my big technical book, I'm saying use common sense. Now, caution. Everybody likes simple. You should always start simple, but the price of simplicity is tunable parameters, and tuning is hard. Now, designing policies, it's not a matter of just taking which one's best. It's more complicated than that. Yes, solution quality matters, and how well it works on average matters. That's generally what we mean by best. But if there's variability, hey, what's the worst case performance? That's an issue. How computationally complex it is. Stochastic lookheads can be computationally very expensive. So can VFA-based policies. Do they always return a solution? By the way, some of this stuff is complicated. It doesn't always work. Transparency, this is a biggie. Can I explain why it made a choice? So when you're saying, hey, I want to pick a supplier for this product, I might want to say, hey, what went on behind that choice? Methodological complexity. You've got somebody in your data analytics team who has to program it up. How complicated is it? If you've got like 3 months to get the project done, are you sure that you can actually get that algorithm working in 3 months? And then the data requirements. Now, testing policies, there's two ways to test. One is, I'll call it a digital twin. I like to call it a simulator. It really needs to be something like a digital twin. It needs to mimic the actual company. Now, I like to use this. I've always built simulators in academic because as an academic, I don't have anything else but a simulator. But people in the real world often do not have the time and the budget to build that simulator, okay? So you have to pick which projects you're going to build a simulator for because there's really the payoff. A lot of times the way we evaluate policies, in fact, the way we're always going to evaluate a policy is in the field. And something that we need to spend a little bit more time with is recognizing that once we dump it in the field, we're not entirely done. And this part of the process has not gotten enough thought from the research community. Now, I've built simulators. Here's a multi-agent simulator for Pratt & Whitney that we built. The data is artificial data, but we could use this to play what-if games on different configurations and different products and different suppliers and that sort of thing. Now, the simulator that we built, Optimal Dynamics Use Simulator, I originally built at Princeton under funding from Schneider National. We spent years building this. OD, every time they land a new company, they use history and they have some fancy processes now put together where they can get this thing up and running and refined quite quickly. And so we very much depend on having this simulator for every single company we work with. So we've really automated the process of getting this tuned because we need this to play what-if games on tuning parameters. Now, as you build models, there's a process between, hey, what type of policy we do, because we see that policies come in different flavors and different levels of complexity. But also so does the model if you have a simulator. So I like to recommend this climbing the ladder approach. Don't make the policy any more complex than your model. As your model gets more realistic, turn around and say, hey, is my policy really addressing all that? Okay, so now I'm going to switch gears to forecasting. This is a little small topic that's very important in the business community. Here I am talking to a company. It was a candy company, and they were talking about how they have to deal with this peak called Halloween. Now, if they had a lot of production capacity, planning for the peak is really not a big deal. But nobody has that much production capacity given this demand pattern. Much more likely it might be around like this, and that means you have to plan for the peaks and you have to start producing in advance of the peak. So you might look ahead and set up an optimization problem to optimize the planning, the production planning, using a forecast of the future. Now, given this model, you can sit at time t, look in the future, optimize, roll forward, update your estimates, roll forward, update your estimates, and solve this. This is basically a more complicated version of Google Maps. Now, what we're doing here is we are using a point forecast. We are using a deterministic look-ahead approximation that uses a point estimate on future demands, the lead times, the yield of the production process. Question is, how are we handling uncertainty? Real-world demands tend to be very random. And when people say that they need a forecast, invariably they mean a point forecast. Now, the problem is we don't really know what the future is going to be. We don't know what the demand is going to be because it can depend on a variety of things. It really is useful to think about building a probability distribution, and it's not that hard over time to turn this into a probability distribution because you just have to keep track of how often you're off and how far you're off. Now, this is starting to become something that's been adopted in industry. This is a nice company in Paris, Locad, and they've done a lot of work with probabilistic forecasting, and so they're looking in the future, dealing with the uncertainty. Here's another newsletter from Decision Brain, why supply chain optimization often falls short in the real world. What they're pointing a finger at is ignoring variability in the supply chain, and variability can be quite significant. There's so many sources. And so their article rolls through comparing single point to variation base, cost of ignoring variability, and 4 practical steps to smarter optimization, incorporating variability and uncertainty. So, planning into an uncertain future, the value of accuracy in a forecast depends on the effect it has on decisions. Having a perfect forecast doesn't necessarily add a lot of value, and you're not going to get a perfect forecast. Making your forecast 10% better, the value of that depends on how it changes a decision. There are 2 general ways to handle uncertainty, and I've covered these in the 4 classes of policies. Use a policy that plans into an uncertain future, so VFAs or stochastic DLAs. Now, these are the most complex policies favored by academics. I can think of real-world applications where absolutely this is the approach, but there are other approaches. You don't have to do a stochastic look-ahead policy. You can use a parameterized policy, deterministic, that is tuned to work well in a probabilistic environment. Basic order up to policies can be tuned to handle random demands. We might use a deterministic look ahead, but introduce slack time and buffer stocks. And there's other ways to put in parameters into a deterministic model, but then you have to tune it. And you have to tune it in a stochastic environment. Now, I've seen companies that have tuned it using the field. Okay, special cases, but very important. Companies that plan energy generation for the grid use that approach. Okay, but in practice, what's happening in the field is that most people, they may do some ad hoc, pull a parameter out of thin air and use it and say, oh, it looks good enough, but then they're not updating it. So we need more attention to this part. So a deterministic look-ahead policy, let's imagine we're Google Maps, and if I'm at node 2, maybe I'm going to follow this path, and so what that means is if I'm at node 1, I'm going to go to node 2. I like that path. That's good. But what if I change the path out of node 2 to follow something different? Back at node 1, I might go, oh, well, if you're going to do that path, I'm going to go to node 3. So the decisions you make in the future can impact the decision that you make now. Now, let's say we have one of these messy logistics problems. So here's my inventory thing, and what happens is at time t prime, I learn about the storm. I see the storm coming in, but in order to avoid a shortage, I can air freight just enough inventory to avoid a stockout. Now, that's fairly simple if it's time t prime and I know that, but what if I'm at time t? And so I don't know that it's happened yet, but I can think about that it might happen, but then I also have to think about what I might do if the storm actually happens. So this is where we say, here's a decision, this is where we are now, and I'm trying to make a decision, but then something random might happen, after which I'm going to make a decision, and then other randomness might happen, and then again I make decision, and then more randomness. And so I have this process of not only dealing with uncertainty in the future, but making decisions in the future. Now, if I'm making the decision now, I want to plan into the future, I have to realize that a human might be making the decision now, but I'm going to have to use a computer to make the decisions into the future. I like to refer to these decisions in the future as coming from what I'll call a policy within the policy, because I'm using a look ahead policy. I'm sitting here planning my orders, thinking about that the storm might happen and what I might do if the storm happens. So, uncertain futures are a part of reality. Don't ignore uncertainty, model it. The challenge is not making uncertainty go away. Instead, it's necessary to anticipate uncertainty and recognize you can make decisions in the future to respond to different outcomes. There is no single way to handle uncertainty. This requires combining knowledge about a problem with an understanding of the different methods for making decisions. Thank you. Once again, this is my link to other technical material.